Hi, this is Professor Dickerson. I've put together a series of 5 videos to lead you through the essentials of one sample hypothesis tests, both for a single proportion and for a single mean. These tests will be very important starting points in statistics too, because we'll be discovering more complex tests for more complicated data sets. So generally in statistics, there's some population out there that we'd like to know more about. Suppose all people living in the United States. However, that population is so large that it's generally impossible to collect data on every member of that population. So what we choose to do instead is to take a sample and compute sample statistics to describe what happened there, and then use those sample statistics to make an inference about what is true of the entire population. So hopefully you're familiar with confidence intervals already. So those are used to estimate the value of a parameter. Like, for instance, what's the mean age of all people living in the United States? We could estimate that and come up with an interval estimate that hopefully contains the true mean age inside the interval. What we'll be doing now, though, is another type of inference, which is hypothesis testing. So there, some claim is being made about the population, and we're going to see how the evidence in our sample either aligns pretty well or perhaps doesn't align with that claim. So for instance, maybe someone says that the mean age of people living in the United States is less than 35 years old. So we can see how our sample stacks up to that and make an inference that perhaps there is strong enough evidence to support that claim, or maybe there's not. So I use a 7-step approach to hypothesis testing. I've seen textbooks with as many as 10 steps. I've seen as few as 4. Generally, we're all looking for the same stuff, so don't sweat too much about the specific numbers. This video is going to cover step 1. We're going to start our hypothesis test by stating our hypotheses and making sure it's clear we know which parameter is really being tested there. So anytime we do a hypothesis test, we need a set of hypotheses. There'll be 2. One is the null hypothesis, symbolized H0. So you'll see why in a little bit, but it's crucial that this null hypothesis has some kind of equality in it. That is, we're specifying something specific that might be our prediction. So keywords to look for in a written statement would be is, equals, no difference, no change. They're all kind of saying the same thing, that one thing is equal to another. The other hypothesis, the alternative hypothesis, symbolized HA, or sometimes people use H1, that's going to describe a type of difference that might exist. So here, not equals, that's one possibility, perhaps is greater than, or perhaps is less than. All right, so notice that the null hypothesis and the alternative hypothesis are complementary. There's no outcomes that belong to both. It's got to be either one or the other. Also, we're going to keep in mind that these hypotheses describe the population or populations as we get to more complex tests. They're not describing what's happening in the sample, because the sample is something we can tally up quite easily. We can compute the sample mean. That's a trivial exercise. What we really want to know about is perhaps the population mean. All right, so I've got 3 statements. For each one, I want to have you consider what parameter is relevant here. And does this statement sound more like a null or an alternative hypothesis? Let's go through the first one together, and then you'll have an idea what to do for number 2 and number 3. All right, so over half of US adults are married. Okay, so we're looking at that statement and think about, well, what's the variable here? What is going to vary from subject to subject? So we're looking at, are they married? So they might be married, they might not be. So that's categorical data. So at least for these one sample tests, if we have a categorical variable, we're going to test the proportion. So what proportion of US adults are married? And the claim here is that it's over half. Okay, so the parameter, what proportion of all U.S. adults are married? And since we're testing that it's over half, that's some kind of difference. And differences go in the alternative hypothesis. All right, so why don't you think about number 2 and 3, pause the video if you need to, and then check your answer in just a second. All right, number 2, we're thinking about the highway fuel efficiency of Toyota Camrys. So that's a numerical measurement, 33 miles per gallon, for instance. So if we have a single sample of numeric data, we are going to be testing the mean. The mean of what? Well, the mean highway fuel efficiency of all Toyota Camrys, not just the ones in the sample, but the entire population. Examining the statement a little more closely, it says they have a highway fuel efficiency of 33 miles per gallon. So it's essentially saying that that efficiency is equal to 33 miles per gallon. So since it's a form of an equality, then that would make it a null hypothesis. All right, number 3, streaming television services such as Netflix and Hulu are used by more than 6 out of 10 American households. So think about what's the variable here. We're thinking about, well, who uses streaming services and who doesn't. So that's categorical data. Hence, we'll test the proportion. Proportion of what? Well, we're looking at American households, so all of them, and what proportion of them use the streaming services. This one's a lot like number 1. We're also claiming some kind of difference, in this case, used by more than 6 out of 10 American households. So since we're testing for a difference of more than, that would be an alternative hypothesis. All right, in order to get the math set up properly for our test, we're also going to need to express these hypotheses using symbolic notation. So remember, the symbol for a population proportion is P. We'll use that if our data is categorical. Whereas if our data is numeric, we would test the population mean, mu. All right, so you'll see we set up our hypotheses using that symbol for the parameter we're testing on the left. My example here is P, because we're testing the proportion of US adults that are married. The null hypothesis, this is pretty easy. The null hypothesis will always have an equal sign in it. So we want to test that the claim that over half of US adults are married. Well, the complementary statement there is that, well, it's not over half, it's equal to 0.5. Right? Our alternative hypothesis is going to express some form of inequality. So there's 3 options. We might use the does not equal sign if we're looking for any kind of difference, either up or down. Sometimes we might test greater than that number, which is appropriate here because we're testing that over half are married, so we'd expect a proportion greater than 0.5. And then in another situation, we might test that it's less than some number. All right, so I've got those symbolic hypotheses, and next to them or below them, I should identify, well, I've got this letter P here. What does that represent? So in this case, P represents the true proportion or population proportion of all US adults who are married. All right, here's another example. So for number 2, the claim was that Toyota Camrys have a highway fuel efficiency of 33 miles per gallon. We said that that sounded like a null hypothesis because it's stating that it is 33 miles per gallon. So our null hypothesis would be mu for the mean equals 33. And in this one, there wasn't any indication given whether we're interested in if this efficiency is actually less than or actually more than 33. So since it was kind of open-ended, we could do this using the does not equal sign. We'll leave it open to both possibilities. Okay, so mu does not equal 33. All right, and here mu represents the population mean highway fuel efficiency among all Toyota Camrys. Right. We'll see why this is the case in an upcoming video, but essentially the idea is that a hypothesis test is going to measure evidence against the null hypothesis. We're able to do that because a specific prediction was made. So for this set of hypotheses, p equals zero point 0.6. If you recall the idea of the sampling distribution for a parameter, the sampling distribution for a proportion, we know that if the proportion really is zero point 0.6 and we take lots and lots of samples, our sample proportions are probably going to be generally near zero point 0.6, but not probably exactly zero point 0.6. Right, so that would be expected due to sampling variability or sampling error, some call it. However, if we saw a sample proportion that was wildly above zero point 0.6, that could be interpreted as evidence against the null hypothesis, and in turn in favor of the alternative. Okay, so we'll get to the actual measuring of the evidence in the upcoming video. All right, so where we're going with this, we have two hypotheses. That sort of corresponds to two possible outcomes for hypothesis test. So for every test, we're either going to go down the left column or down the right column. So on the left, suppose we find strong evidence against the null hypothesis. That's going to lead us to believe that the null hypothesis is not true. We should get rid of it, or as we say, reject it. And if we do reject it, because there were only two hypotheses to begin with, and we throw one away, by process of elimination, we can then support or conclude that the alternate hypothesis is true. Okay, so that's on the left. On the other hand, on the right-hand side, what if we don't find especially strong evidence against the null hypothesis? Well, that would say that we can't really rule it out, and the terminology is we fail to reject it. So if we can't rule it out, there's still two hypotheses. We haven't narrowed the field any. So this is kind of an unsatisfying outcome. We can't really be certain which is true. You want to be careful. A common mistake is that people want to say that the null hypothesis is true, that we support it in some way. And that's not quite accurate. Just because we fail to rule it out doesn't mean that necessarily it's true. We'll explore this a little bit in video number 2 coming up shortly.